All right. Thanks for joining us today. We've got Bruce Rendall from Ventura County, California, and he's going to talk about some of the cool things they've been doing with PostGIS there. Bruce, do you want to tell us quickly how you got started with PostGIS?
Uh, I actually got started with PostGIS in 2005. They did a wonderful online mapping interface back then that even before Google Maps, where everything was done with WMS, and all the vector graphics was done with SVG, and the SVG was generated completely out of PostGIS. So it was quite a project back then, and have been involved with it ever since.
Oh, wow. That's great. Wow. Sounds like you go way back. All right. Well, we're excited to hear your talk. So go ahead and start your screen share and take it away.
Okay, thank you. Hi, again, as she said, I'm Bruce Rendall with Ventura County, and we want to talk about some of the applications we're using with PostGIS in Ventura County, in particular on our web flood warning system. So we got a few applications that we want to talk about. We'll start with the general and then go on to the gory details later. The slides are available shared at that shortened URL. So I'll give you a second to do that. Then we'll move on. First off, to talk about our flood warning system, it's dominated by event-driven point data. In other words, a rainfall gauge. As it measures rainfall, it has a bucket tip. And so that's an event that is stored in a PostGIS database. We also have stage, weather, all other forms of information. The PostGIS database stores all the data. And for most of the things we do table functions to create the pivot tables. So in other words, looking at a string of bucket tips for a rain gauge, we need to convert that into a table that shows how much has it rained in the last 15 minutes, the last 30 minutes, 1 hour, 1 day, etc. And we create those pivot tables in PostGIS. And then because those are points, we have the lat long information. And PostGIS converts it all to GeoJSON. And it does it very, very easily now, especially now. Over the last few years, they've had some tremendous improvements to how we do that. So why do we use GeoJSON? It's because it's compatible. You can just drag the file onto QGIS, as most of you know. Even CartoDB supports it, both as a file and as a URL. Lots of web libraries, including d3.js, which we use extensively, use it. Also, Leaflet supports GeoJSON natively. And of course, you can even go right back into PostGIS from those files. So it makes it very, very compatible with a lot of different software packages. So what we do, this looks pretty typical. The large section in the middle is where we generate our metadata. So this information here, the CRS, the metadata, when we created it, we do it all in UTC, the host that created it, a description of the GeoJSON, where it came from, and the view. So that generates our GeoJSON automatically on the fly that we update every few minutes, depending on what it was. One thing to note here, if you're trying to do this, we had to add this little file section here called coalesce. Many times our data is based on view. How much has it rained? How much flooding impacts do we have? And sometimes those views can be empty. We don't have any forecasting. We don't have any forecasted rainfall. We don't have any forecasted inundation. We don't have any forecasted impacts. And if you just use the standard conversion to GeoJSON, that empty file will throw an error. So we had to use this little coalesce function to add the little closed square brackets instead of the word null, which helps out a lot when you're trying to debug and everything looks good except for OpenLayer says it's an invalid file. So that's a little hiccup that we found during this process. So what we do is we then put the GeoJSON file, and this is typical. This is what we typically look like when it rains, which it doesn't lately a lot right around here in Southern California. But then with the GeoJSON file, we have the location, we have the information, we have a lot of metadata along with it, and we can color code and see on the map how much it's raining, where it's raining, and get a lot of information very quickly on a web page just by reading the GeoJSON file the post just created. In the background, which we'll talk about a little bit later, in addition to the rainfall totals for the background images, we can have our stream locations and previous fire locations. Both of those coverages are done with map vector tiles, map box vector tiles. So we can talk about a little bit about that later, but quite a usable interface that we can use. We get a lot of people to take a look at for our flood warning system. Now, the next detailed application I wanted to talk about is flood inundation. We want to say, hey, with these predictions and the models we have, how much inundation and where will the flooding occur? And this was quite an involved process that was done with PostGIS. First off, we take hydraulic models. So we estimate the depth at various cross sections. There's lots of standard models that do this information, both 2D and 1D. Then we convert the cross section elevations to a continuous surface. That's a raster operation to interpolate the water elevation. We then do the standard intersect the surface with the digital elevation model. Anything that's above the digital elevation model is an area of inundation. It can be quite noisy depending on your raster and how flat your digital elevation model is. So we clean up the boundary, remove the interior holes, we smooth and simplify. So we get a nice clean boundary of potential inundation at a flow value. Then we store that boundary in a PostGIS table with the location ID, a minimum flow, a maximum flow, and the boundary. And then, as we say, rinse and repeat. We do this at numerous different flow values to have it in like a library of inundation values at various inundation boundaries at various flow values. To give you some kind of idea of what this is, typically this is a cross section at all these various locations. The model takes the flow and generates an elevation at each cross section. This comes from HEC-RAS, HEC-2 for those of you who are involved in the flooding systems. And we want to convert those elevations at the various different cross sections into a continuous elevation to get some kind of a boundary. Now, this is the first step. We'll take the inundation boundary model and the cross section at various locations, and then do a smooth interpolation between the cross sections. And we grab the information using our favorite tool, our foreign data wrapper. We just point to the shapefile, which has all the information at the various, it has each one of the cross sections. It has in a shapefile, and it has an attribute that takes all the shapefiles and has the various attributes from the shapefile. And we just put it into our server so we can read the shapefiles directly. It's real handy to have that. Not only do you have the foreign data wrapper, but you could actually go back and edit the shapefiles if you want to clean up some of the information on it. Then we can take the inundation boundary from those shapefiles and say, well, there's a outline of it. It's, as we said, a little choppy. You can see some various small holes because it's very flat in this area. Additional holes here, kind of a choppy cross section, and some other information that we want to clean up. With some magic of PostGIS, we clean it up, remove all the holes, and get a much smoother boundary from that. And that's pretty standard SQL command that we have worked with and played with. So we can go from a rough estimate back to a smoother one that we have in PostGIS. The method we do this, first off, with the inundation, we buffer everything just to give it a little bit smoother outline. Then we just take the boundary as you blow up the boundary using ST exterior ring from the geometry. And then you transform it with little smoothing functions and group it all back together. So we have a smooth boundary like we showed before. Again, this is kind of pseudocode. If anybody wants the detailed SQL commands, I'd be happy to give it to you. And what that comes out with is a typical boundary in a PostGIS table. The table is, you have an ID, a feature ID, you have a lower flow and upper flow, a site ID. This is a location. In this case, 608 is the lower Ventura River. And then we have a geometry associated with it. And we have 40 or 50 locations where we have these inundation boundaries generated by PostGIS, and at up to about 15 different levels of inundation. So now you have the boundaries, the ID for the location, and an attribute chain of the flow that was generated. To see this conceptually, here is an example where we did a inundation boundary. We had a whole series of them. All of these are in a table. And each one of the boundaries, here is the inundation boundary at 5,000 CFS. As you can see, very small. And as you gradually go up in flow values, in this case, 25,000 CFS, you can see the inundation boundaries gets larger and larger until we get to the very larger areas, including all the extensive inundation at 75,000 CFS for this particular location. So we have a whole library of values that include the GIS boundaries stored in PostGIS. Then, as you can imagine, it's a simple matter of just grabbing at each location, find a maximum forecast, and then just show the inundation boundary due to that particular forecast. So you can show at various different locations. This has two boundary sets, one set for the Santa Clara River and one set for the Santa Paula Creek. We do overlap, which is kind of ugly, and we wanted to make a clean, uniform process to do that. So again, with the magic of PostGIS, we can simply snap back and forth and eliminate all the overlaps. We do that with a recursive query. So it goes much better from this to this, and using some techniques to make it clean and looks just like that. We have no overlaps on that. That query is, as I said, a flood inundation. It's a recursive query. We start out with the first row, we call row 0. That's simply the union of every single bed of inundation. And then one at a time, we work our way down through each one of the inundations based on the flow value and take the intersection from the total value and then return the difference between what we had before and what we took out this time. And that's what I call leftover. So we have geometry and leftover. And you walk through the recursive query all the way down to the end where it's just the only thing that's left is the last bit of inundation that doesn't intersect everything else. Fun little thing learning how to do recursive queries. We also do something very similar with the flooding map. Here we have, these are point locations. And again, we have a list of these are the locations and the action level. In other words, what level of flooding will trigger that location. And again, that's a query. Take the maximum flooding estimates from our models or forecasts. Do any of those exceed this level of inundation, action level of these hotspots, as we call them? And if they are, throw them in GeoJSON file and they're displayed on the map. All the information about the locations are included in the GeoJSON file. So in the web application, you can just click on it and see what the information is and what the potential is. Here that also shows on the same map the potential flooding inundation. Okay, now changing subjects, we want to also say, are we affected by an earthquake? So from the USGS, you can get a comma separated file of every earthquake in the world at various locations in a comma separated file, text file from the USGS. It's updated every 5 minutes, so we grab it every 5 minutes. Now, without going into a lot of detail, what the Corps of Engineers, our location, a few others have said is obviously the bigger the magnitude, the more impact on a facility could happen. And they came up with, if it's so many miles away with this kind of magnitude, you want to check it. If it's a bigger magnitude, it can be further away. And it actually came out quite a linear function. So we just said, if the magnitudes, you subtract the magnitude minus 3.7, multiplied by 3.8, that gives you miles that could potentially impact you. So all these calculations can get a little bizarre, but the fun thing about it is we can do all of this in PostGIS. Well, the earthquake data is in CSV format, so connect again through OGR FDW, the foreign data wrapper. We already have the existing facilities are in a PostGIS table with lat long, and we can compute, if you generate the points from those, cast them to geography instead of geometry, then ST distance gives you the distance between those in meters. And that just gives us a list, again, a view of any potential facilities that if they meet that criteria, they should be inspected. And we have a web page summary of the facilities that need to be inspected. And we also send an alarm via Twitter. So here's the pseudocode for that. First, we do the wget to get the latest CSV file. I'd like to do a direct connection with curl or some other methods, but I haven't figured out quite how to do that. So we link our foreign data wrapper to where the CSV file is stored. We create a foreign table that connects to it, and we now have a table that's directly linked to the USGS information. So now we do some more PostGIS magic. First off, we have the facility location. There's all the various locations that we're concerned about. Two things you notice, the easting is wrong. It should be a negative number. So make sure you get the pluses or minus. Most everybody in the US just gives a positive number in it. They assume that west is, that you know what west is. And yes, we have locations down to the nanometer for the northing and easting, but that's the data you get. And here's a typical location, a map of earthquake locations. I did this snapshot last week, and there's lots of very, very small earthquakes. Nothing that constitutes even anything you could feel, but they just show up on the in the table for that. So here's the tricky part. How do you trigger an alarm from a query? And if you do this every 5 minutes, how do you prevent the alarm going off every 5 minutes? Because the file from the USGS is all the earthquakes in the last 2.5 weeks. So first off, we just list all the facilities impacted by the earthquake. That's in one query, and it goes to a web page, and that shows up for a couple weeks. And we can take a look at that. Step two, we have a side table called alarms. And the alarms are those earthquakes that triggered an impact. So let's see, all the facilities impacted by the earthquake not included in that previous alarms table. The result of that step, we send an alarm to Twitter so we can see, hey, we've got an alarm, we need to check our facilities. And then right after that, we add that earthquake that was generated, any earthquake that was generated in step two, add it to the alarms table. So the next cycle, that alarm will be, that earthquake will be in the alarm table, and it will not list a new alarm. So you fire it off in the first 5 minutes, in the first cycle, and then 5 minutes later, it's removed from that. This is kind of a bad flow diagram, but you get an earthquake list and the facilities list. And the first step is, from that query, do we have any affected facilities meet that criteria? If it's yes, you go to a web page, and that web page shows up for quite a while. The other step is you take those same two, and then are the facilities in that, are there any affected facility earthquakes not in the including the previous alarms? If it's yes, send out a Twitter alarm. And then also from that, add it to the alarm table. This prevents the alarm from going on over and over and over again. So this is what our web page looks like. This was a series of earthquakes back in 2019 that rattled off most of Southern California. And you can see we have a table saying what facility it is, where it is, the name of it. the earthquake that impacted it, the magnitude, and the trigger that criteria that would have caused it. So we can see that even though it was a pretty significant alarm, it was just barely over the criteria in most cases. So additional future plans. Obviously, since we can just store those flooding inundations in the database quite easily, we just say, well, add in inundation levels to more locations, better models, better inundation. So we can supplement our flood warning system with a more fine-tuned warning system. Try to do a direct notification to the USGS data source instead of trying to download to a table and then point to the file. We want to do a direct connection, and we're working on that. We want to expand this automatic notification to other threats, i.e., if we run a model and we say we've got several hotspots and several inundation, maybe we do the same information to say on Twitter, we have potential flood threats. Another one is, as you saw, we did vector tiles to our web map, and which has done very, very well. The vector tiles come out of PostGIS, but they go through GeoServer to do the caching on our 2 servers that do that. And we want to continue to review new technology to improve our displays and reports. That's constantly changing every month that we look at it. And finally, look to new ways for customers to interact with our data. We do analytics on our web page and see what pages they look at, what they use the most, and make those faster, more efficient, and more useful information. And with that, that's the end of my presentation. Again, the website to see that kind of information is vcwatershed.net, and the flood warning system is vcwatershed.net/FWS, but you can get to that. And again, the copy of my slides here is at that same shortened URL. So that's the end of my presentation. Thank you.
Thank you. That was really interesting. Thanks so much. Appreciate your talk, Bruce. Oh, just quick question. I saw you had some really nice queries. Are you a PG admin user, or what's your query writer?
PG admin. I mean, PG admin was really useful for me at first, but the ability to display it on top of an open layers map is just huge. That just made things so much better.
Yeah, yeah. So I had one question. You have some really interesting kind of things that you've done, for kind of Ventura County. Is there like a group of county geospatial engineers? Like, do you guys share this kind of information, or did you just do this all on your own and you're all kind of separate?
Well, we did it all on our own, but we work very carefully with all the local agencies.
Right.
So in other words, you'll see our rain gauges, but on the map, you'll see the rain information from both Los Angeles and San Luis Obispo and Santa Barbara County, because we cooperate with our flood warning system to get the data. And so we take their information, import it from their gauge information in their software, and we put it in there so we can put a display, which is really helpful, not only for them, they can see it, for our local National Weather Service office, but as the storms move down through the area, we can see as they progress from there. All the information we've shared with a lot of other agencies, and ideas have gone back and forth with not only our software vendor, but other agencies who do similar flood warning systems.
Right, right. That's interesting. I was also wondering, like, so you have a lot of modeling for flood events. Like, have you had the opportunity to compare the models to actual flood events, or have you not had like enough rainfall to even be able to do that?
Well, we've been doing this quite a while, and it hasn't had a lot of rainfall in the last couple of years, but surprisingly, we took a look at the models, and sometimes the inundation levels were higher than we thought they were. And it wasn't due to the difficulty of the web page or the models or anything else. Is we literally had sediment build up in the stream. And so there's an idea of, hey, what happened here? And they go, you had about 2 or 3 feet of deposition in the stream, and it's much, much higher than we thought it was. So there's that constant need for updating and changing the models and information.
Right. Exactly.
And that's where it can be really nice, because you don't have this one big inundation boundary for everywhere in the county. You just said you have it at various locations. And maybe some
Right.
sections you don't need some updates, but other ones you do need updates. Rerun
Sure.
the model, redo the boundaries, put those, take the older ones out and put the new ones in, and you have an updated information library.
Awesome. Well, thanks so much. Super appreciate you coming by today.
Thank you very
Take
much.
care.
Appreciate
Yeah.
it.